one. All right. Any other questions? So again, for those that are watching this asynchronously, the quick update, since I forgot to record this, if you visit this website during the class periods and maybe for a short period after, you can post questions that I can try to address. You can post these anonymously. If you're happy to stamp your name on them, just post them in the discussions. And then this slide basically gives you an idea of what's due. ICA A2 is due on Thursday. Lab 1 is assigned. It'll be due on Sunday. It's a very short lab. And the homework B1 is already available if you'd like to get started on that. Great. All right. So it looks like we have some resolution of the Canvas issue. Okay, thanks for that. All right, so let's get started then. So this lecture today, we got this week we have introductory lectures. This one's an introduction to modeling in general and a little bit of simulation modeling, and then stochastic simulation modeling, and what the heck we even mean by stochastic simulation modeling. We talk about it on Thursday. So to motivate all of that, this will be a little circuitous, but so my background, back decades ago now, I started as a software engineer. I worked in telecommunications and networking, did some open source software development at the Linux kernel and some other things like that. And then I decided to get my bachelor's degree. So that was back in a time when there weren't a lot of people working in these areas. And so you could get started in engineering actually before you even go or getting a bachelor's in engineering. And so it was a very different time back then. But then I took my BS and I decided that I wanted to be a purist, and I would go in and I would be a double E, and I would study electromagnetics, analog electronics, robotics, control theory. I, for a while, was convinced I was going to be an antenna designer until I got interested in something called control and the mathematics that were involved in control systems. And then that got me into these bio-inspired algorithms for control. So then I took so that was up through my doctoral work, which is in my PhD. And from then, I actually got a postdoc in computer science, and I did something called software verification. And I also worked on autonomous urban vehicles. And then I took a second postdoc after that, working in biology, working in behavioral ecology and collective behavior. That's when I learned to work in a wet lab. And so I learned how to work with organismal models. And so I worked with ants primarily. And I still have students now that do field work, go off to Australia and Panama, and they do field work with these sorts of things. So went from engineering all the way to kind of biology. And so it's a mixture of kind of engineering and science. And now you see me here teaching industrial engineering courses. And so this may not seem like a traditional path to industrial engineering, but I'm bringing this all up because it really motivates a question of what is industrial engineering? And so, this is something that I think a lot of people have trouble with. And so what I want to try here, and hopefully time will permit, so we've got a good chunk of people in the live section here, then what I'd like to do is put us just for about 1 or 2 minutes into a couple of breakout rooms. And I want you in your small breakout rooms to just come up with an answer to what is industrial engineering. So I'm going to assign you into, say, 12 rooms, maybe 13 rooms. And while we'll be in breakout rooms for about, say, 2.5 minutes long. So quickly come into your rooms and then try to answer this question. We'll bring it back together and then we'll keep moving from there. So opening the rooms now. And I might pop around to all of the different rooms. All right. I heard some great discussion, so I'm going to go back to the share screen here. Um, and rid of, all right. So does, let me try to bring up my participants list again in chat. So does anyone either in the chat or via audio or video have an answer that they'd like to share that they came up with a good, I hear, so one in the chat here, the social science study of differing processes and systems. So I see that that's this word process and system, that's kind of cool. I think it's interesting that the word science was used there. I see optimization of processes through business practices and data analysis. Business is important. So yeah, that's kind of it. It seems to be something that shows up a lot in these sorts of things. Data analysis, data again. So something somehow is tied to science, which is kind of interesting there. Anyone else have an answer that they want to share of what is industrial engineering? I see process improvement and efficiency in many different industries and departments. When I popped around to a bunch of different rooms, I heard people say things like optimization came up a lot. So improvement, optimization. So something about operations that we can make an intervention in the world, and we don't know which intervention we can make in our human practices, but maybe industrial engineering shows us how to make that intervention and then make that process better. So that I definitely feel like was kind of a common thing. So that's good. So let's keep those thoughts in mind, and then let's then think about. So without going into breakout rooms here, but let's just maybe think about just for a second each individually. What do you think? So there's some people talked about. I love the first answer, the social science study of differing processes and systems. I see your science there, and so then the question might be is like, what really is the difference between science and engineering? And again, without going into breakout rooms, does somebody have, if they were, I'm sure some of you have, maybe when you're choosing your major, you had to sort of think about this, like, in high school, they said I was good at science, but I wasn't quite sure it was right for me, so I decided to go into engineering. And so you've had to struggle with this yourself. And so does anybody have an answer? What is the difference between science and engineering? Does anybody have anything they'd like to personally share?
I I think personally that engineering I feel like is more practical. There's more application to it, and then science is more of the studying and like it's more academical.
Interesting. So I hear from that answer, science is a study and engineering is kind of an application. And I hear a couple other things. Science is more theoretical. This is in the chat. Science is more theoretical, research-based, and engineering is putting that knowledge into use in real-world applications. Applications make sense. Engineering uses science in order to create or modify something. These are great answers. These are great. So here's just one definition that I picked up out of Merriam-Webster. Science is such knowledge or such a system of knowledge concerned with the physical world and its phenomena. In other words, a scientist has to grow a body of knowledge about the natural world by making inferences from data gathered in experiments. And so a scientist says, I do not understand how this baseball flying through the air works. And so I am going to gather data. I'm going to throw a bunch of baseballs and I'm going to develop a theory. And I'm going to then use that theory to generate predictions. And those predictions I will then test in experiments. And if my experiments behave like the predictions, it helps me validate the theory. If they reject the theory, then I move on to other theories. But it's about figuring out theories that are good surrogates for whatever the heck the natural world is. That's science. It's taking data and turning them into knowledge about the natural world. Now, if we flip over that engineering, follows the answers you guys have already said. The application of science and mathematics by which the properties of matter and the sources of energy are made useful to people. And that is where the business part comes into play. So some of you said industrial engineering has to have a business component. It's my claim that all of engineering has a business component. I mean, the material scientist might be interested in the thermal properties of a particular material, but they're not interested in it because they're interested in materials. They're interested in it because they're going to make a buck off of those. They're interested in it because they need to find a material that they can produce at mass quantities that they can put into a marketplace for people to use. And so it's about that making useful to people. So regardless of what type of engineering you're doing, the instant you cross into engineering, you have to be, what is it useful to people? To be useful to people doesn't mean you just already have the knowledge, but you have a way to apply that knowledge and scale it to a point where you can actually disseminate a product that comes out from that knowledge. And so an engineer is a consumer of scientific knowledge. So I think all of you sort of said this, but so then I want to walk you through sort of a line of thinking then. It's like, okay, so a chemical engineer depends upon knowledge from chemistry. And so I've got on the left side of the screen here, I've got some chemistry, done some experiments, learned some things. And then a chemical engineer builds things, they're recycling processes, soap, toothpaste, whatever. So we've built stuff from knowledge gathered from those sciences. An electrical engineer maybe depends upon knowledge from physics. So the physicists go over, they go out, they develop, and validate laws of electromagnetism, Maxwell's laws, for example. And then from there, you get game controllers and microchips and light bulbs. So you're making use of that. Now the question then, when we talk about industrial engineering, well then what the heck is the science on the left-hand side of the page for industrial engineering? Who are the industrial scientists out there? Does anybody have something like the volunteer in the chat, for example? If I had done a better job structuring the beginning of the class, then we'd probably do this in breakout rooms. But I'm learning to pace myself here. So does anybody have sort of an idea of what are the, like, electrical engineers maybe lean on the physicist, chemical engineers lean on the chemists. Who do industrial engineers lean on? What is the science or sciences of industrial engineering? Anybody know? Anybody have an idea? What science do you see in your classes, if any? I see social science. I think that's an excellent one. We'll get into that. Anybody else have any others that they think of? Statistics, that's an interesting one. Economics, math, stats, data analysis. So seeing a lot of kind of like, what's interesting about stats, econ, math, and data analysis, those things all use data. Those things are shared by the scientists out there. Economists are sort of bundled in with sort of scientists there. So it's interesting that we associate data analysis with industrial engineers in a way in which we don't think in terms of like electrical engineers. Electrical engineers might not even know what a t-test is. They might have had it once, but they never had to use one. You will use t-tests in this class. Systems, so systems is kind of an important, it's like a higher level science. And so, kind of borrowing from all that, these are just some of the things that I throw in there. I think industrial engineers borrow from psychology. I think they care about humans, human factors. They care about, you have a process. Is a human actually going to behave well if you force them into that process? So they care about the individual human cognition, for example. That is something that's important to industrial engineers. Social psychology. So what happens when you put a bunch of humans together in an organization? That matters to an industrial engineer as well. When you're designing a process, a socio-technical process inside a factory, for example, you got to have humans, you got to have machines, you got to think about humans working together. You have to consider all of these different things. And then all of these things come together, psychology, technology, law, ergonomics, economics, they all come together. This systems component that was brought up in the chat there. There really is no one science that we industrial engineers can lean on. We almost have to invent it ourselves. And that is really what we do as industrial engineers. We have to not only consume the knowledge, but we have to build knowledge about these complex mixtures. When you put humans and machines and the natural environment together in one place. You develop systems that science has not ever seen before. There is a theory for how a baseball flies through the air. There is no theory for how a factory works, at least no theory that we can go over to the sciences. But you can't go to the College of Liberal Arts and Sciences at ASU and tell them, like, what is the fundamental law of factories? There is none. They'll look at us and say, well, I don't know. Here's how a flower grows. Here's how to melt a piece of metal. They can tell us these specific things, but when it comes together about these complex systems, we're on our own. And that's why data matters so much to us, because we are building the data. We are using the data ourselves. Industrial and systems engineers are at the intersection of science and engineering. You, as industrial and systems engineers, are going to design experiments, develop models, make inferences about the validity of models, all of the things that pure scientists are doing. You also are going to be designing new processes for how technology and humans interact. And you're going to be making systems more efficient. That is all that engineers are doing. And you have to do them both together. And so you are closer to the sciences than I would say any of the other engineers are. And I think sometimes it feels like you're more divorced from the science because you're sort of several levels of abstraction away from it. You're not a chemical engineer, so you don't have the chemistry that you can say, like, I'm kind of a part chemist. But what you do have is you have the stats. You have the stats and the data, the ability to handle data that other engineers do not have. And you should lean on that, because that is your superpower. You will be able to do things with data that the rest of your engineers will have not had the training to do. And the things you do with data are the things scientists do with data. You are the scientists of engineering. So that's kind of the background for these questions that I'm asking today about, like, what are models, for example. And so this term model, we need to have a scientist's appreciation of the term model and what model means. So our definition of model has to include these models, as well as the models you might be more familiar with seeing in industrial engineering. So why do we call these items that I have placed on the screen models? What is model-like about them? How's that term being used? Does anybody have a good answer to that? So I might call them fashion models, for example. So why would I call them models or fashion models? How is that term being used? Why? Yeah. That's an interesting point. So in the chat, they are exemplars we aspire to. So that is interesting. I think that this is probably true. When you look at this, you say, this is how I'm supposed to dress in order for me to be accepted in a particular group. And so that is probably true in many cases, but that is probably not how they got started into this. So like that might be one way in which they're used now. But initially, when someone asked someone to put on an outfit and stand in front of a camera, how were they supposed to be used? How was the term model supposed to be used there? So a model I see as a generic, so somebody's giving a definition, a representation of a specific system. That's getting a little more generic, and we'll get there. But why these? Why am I calling these models? What do these do as models? So let's, and I'm putting aside the exemplars for us to aspire to. We'll get to there, but let's say more fundamentally, when somebody first came up with the idea of putting clothes on another individual and taking a picture of them, how was that a model? How is that an example? It's an example of what? They're showing how the clothes look on people. That's what I'm looking for there. That's right. So a specific instance that we can generalize to understand these clothes on a wider audience. It represents an idea of how the clothes would look. I don't know if I'd like that jacket. Well, on a hanger, yeah, it looks terrible on a hanger, but let me put that jacket on a real pair of human shoulders. They're not your shoulders, because maybe you can't wear the jacket right now. Maybe you're looking at this in a catalog. But if I put it on some human shoulders, those human shoulders are more human-like than the hanger. So if I put that jacket on these human shoulders, then maybe now you can really evaluate whether you think that jacket is a good-looking jacket. Same thing with the dress. dress doesn't look at all, you know, it's hanging on a hanger, there's a whole half of the torso and the head that's totally gone, you know, but you put it on a body and then suddenly you get a better understanding of proportions. Now notice that that makes the assumptions that the model, the person that you're putting it on, is a good representation of reality. If you look at this guy on the left side of the screen, he probably has more product in his hair than I put in my hair in a week, especially now during COVID. And so, you know, like, you know, he's bent in this funny way. She's bent in that same funny way for some reason. I hardly ever bend that way. In fact, since I've been sitting in a chair for so long, for the last couple of months, when I bend that way, I get immense pain in my back. I would not walk around bending that way, but for some reason, bending that way was how they were chosen to, you know, to take these pictures. So this shows that there is some usefulness in putting the clothes on a human as opposed to just displaying the clothes otherwise. But there are degrees of freedom that can be manipulated in ways that distract us from looking at the clothes. And so if we put the wrong, you know, if we put the, you know, we're modeling the jacket, but we put the glasses on the guy, we put the shirt on the guy, we make him go in a particular position, we can, you know, put his hair in a particular way. And you start saying that, yeah, maybe this looks like an attractive image, but it would not look good on me because maybe my body type is so much different than his body type. You know, maybe I need to lose a bit more weight before I can look at all like this guy. And this is a poor model for what it'll look like on me. Better than the hanger, sorry, I just heard, okay, so one of my Bluetooth speakers for some reason decided to kick on and tell me it was on. So, yeah, so that is eerie. I don't know if anyone can hear that, but let me see if I can disconnect this. Sorry for that. So, fashion models, that's why there are models. They're demonstrating how the clothes work. And I hope everybody can still hear me. Because again, I had this weird audio issue. So animal models. So this is an organismal model, an animal model. This is a mouse model. So this laboratory mouse, it's being in a lab, it's being used in a laboratory. And so why do we call this an animal model? Why do I use that term? The last models I called a fashion model. Why? So now we're kind of using animal in a slightly different way here, but why would this be called a model? And this is how biologists refer to it. This is how doctors refer to it. This is an animal model. Why is the mouse itself a model? Anybody have their own idea? You can offer either through audio or through chat. Anybody? I can wait. What does this mouse represent if models represent an idea? I see less risk in doing it on bigger projects. I see it's representing a human counterpart. I see experimental purposes. So, so I see the focus on the less risk here. So if we talked about, say, a pharmaceutical trial, then someone might look at this and they might say, well, we might want to try a drug on an animal because that animal is a representation of a similar physiology as a human physiology. But we can't experiment on humans for ethical reasons. And so we have sort of a different set of ethics for animals. We do have ethics for animals, but there's just, it's a different set of ethics for animals. And then so this allows you to test those things without testing them on the human. So this becomes a stand-in. It allows us to answer a question of what would happen if we gave this drug to a human. Now, again, like the fashion models, this may be a poor model. You know, like there's a tail that's back here on this. I don't have a tail. Now I do, you know, I am a mammal, so I do have fur, you know, I do have hair, but I don't have quite this much hair. My ears don't look quite this way. So there are a lot of things that are in common between my physiology and this mouse physiology, but there's a lot that also differ. And so we have to be careful about how we generalize and you know, how we interpret these results, but it is better than nothing. So this is a model even though it is an animal. So a lot of times when you hear about models, you think of them as just being mathematical models. This is as much of a model as a mathematical model. So getting closer to maybe models that we're more familiar with, this is the Bohr model of an atom. It looks kind of like a solar system. And so there's a nucleus at the center, and these electrons go around in these concentric orbits. And this was a theoretical model, effectively like a mathematical model for how matter was made up of. When I hold up this coffee cup, what is giving this coffee cup its stuff? It was thought to be this. And for a while, this did a great job in predicting the properties of real matter. But it failed at particular small scale features. And so a lot of people don't realize is that they created other types of models that were similar to this, revisions of it. So the Bohr model, there was this elliptical model that suggested that as you get into these different orbits, then you get more elliptical. And this different model of the atom produced slightly better predictions for certain things in the laboratory until it didn't. So it also failed at particular things, which is why we don't hear about it today. And then now, if you go back to your chemistry courses, for example, you're probably have at least seen molecular orbital theory. And so now we don't think about the atom like this at all. We think about the atom as this nucleus with this cloud of electrons that kind of exist in this sort of continuous space. And as they get up into higher and higher energy levels, then these clouds deform. And they deform in these ways that give them these shapes that don't look at all like any of these things. And this model here is a much, much better predictor of the small scale features of real matter than all of the rest of these. And yet we still teach to, say, elementary school kids, or even maybe high school kids, the Bohr model of the atom. And then over on this side here, we have the so-called standard model from particle physics, which includes a bunch of particles that you see over here. And this standard model includes an electron, for example, just like this one. This is an electron cloud, and these are electrons that go around here. But it's meant to sort of help us understand what's inside. If you combine electrons with other things, can you make other particles, and so on and so forth. So it's meant to answer different questions. And so it's a different model for helping us understand matter. And it is not necessarily inconsistent with the models on the other side of the screen, but it is truly a different model. So as we see, the notion of an electron, of an atom in general, but even an electron more specifically, seems to keep changing. And it leads us to one conclusion as modelers, is that electrons do not exist. Electrons are a tool that have been enormously successful for us to understand matter. They are useful, but they do not exist. We do not need to say that an electron is actually there. There could be some enterprising young graduate student in a physics laboratory right now at Arizona State University that is experimenting with a new theoretical model for matter that does not have electrons. And that may finally bring us even more precise predictions of the properties of matter. And after that would be well tested and established, the textbooks will be rewritten and we just wouldn't have electrons anymore. There's no reason to believe that the successful models from physics will have to have electrons in the future. We just know that the most successful ones now do have this concept of an electron. It's about utility. And likewise, Newtonian mechanics, Newton, guy on the left there, came up with all this mechanics about baseballs flying through the air. Turns out it's all wrong. Turns out that the Newtonian ideas, especially things like gravity, are they don't, the way Newton thought about gravity is totally different from the way Einstein thought about gravity. And yet Einstein's gravity is much, much, much better at predicting things at the scales in which we can now observe with modern technology. And yet, we teach Newtonian mechanics still. Mechanical engineers build airplanes, out of Newtonian mechanics, and everybody seems to be fine. So models do not have to be right, they just have to be useful. And that's finally brings us to a quote that I'm sure you've seen in a lot of other classes. Essentially, all models are wrong, but some are useful. A lot of people misunderstand this quote, and they think that George Box, who's a famous statistician, was criticizing models, when Box wasn't. He was saying, no, 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 it's wrong to criticize models, actually, because all models are going to be wrong. What you really should be doing is asking, how wrong do they have to be to not be useful? So eventually, at some point, your model is going to be so wrong that it just fails to be useful. But things like Newtonian mechanics, despite how wrong it is, it continues to be really, really useful. So the idea is that we do not worry about, is the model true? Because if truth were to be the whole truth, the answer will always be no. All models will always be wrong. The real question of interest is the model illuminating and useful? And I bring this up because in this class, we are going to build simulation models that can always be attacked for being overly simplistic or making assumptions and all this and that. And the real question isn't, did you build, no, because you always can make your simulation model more and more complex, more and more like reality. But the question is, when should you? And almost never is adding more complexity for complexity's sake a good idea, because eventually your simulation becomes as much of an enigma as the real world. Simulations need to be illuminating. They need to show you something that the real world couldn't show you and give you the opportunity to then go out in the real world and test the idea that the simulation has presented to you. So that is what we're building in this. So we're building things that will hopefully be simpler than the real world, and yet illuminating and useful when interacting with the real world. So this is from my own a fortune cookie that I opened up once. This tumbled out of it. Do not seek so much to find the answer, so much as to understand the question better. And that is really what we do as modeling. We are not interested in truth. We're interested in better understanding the problem that has put us here in doing the model. All right, so my general definition for models provide to what models do is models provide answers to what if questions. So I want you to remember that what if here. So I would normally ask an attendance question here. I'm going to skip this for now, but we will have an attendance question later. But just for now, I'm just saying, remember that, I'll go back to that, is that models answer what if questions. You know, what if I were to put on this jacket? Well, here, let me show you the jacket on a fashion model, and that'll help you answer that. What if I were to take this drug? Well, let me give this drug to a mouse. Let me give this to a drug to someone of similar age, sex, and weight as you. These are all models for what would happen if you took the drug. So models provide answers to what if questions. All right, so are there any questions about that, or what I mean by what if models? All right. All right, so the types of models that we work with or that we see in engineering and in science in general. So there are statistical models. So I have a bunch of data, like here, high school GPA is one variable, university GPA and another variable. I plot a scatter plot, and I can do a linear regression. I can plot a line through it. So the model is the line. It is a relationship inferred from data. We are not saying that this is that high school GPA is what causes university GPA. We're not saying that someone who does poorly in high school will necessarily do poorly in the university. We're not saying that doing well in high school is going to prepare you to do well in the university. There could be other causal factors, but we can infer a relationship, and then we can test that relationship. So that's the big thing. This is illuminating because before I plotted this and drew the line through it, I didn't know that there was potentially a relationship there. Now that I see that relationship, I can go out and I can tell high school teachers to do things differently. I can tell admissions people to do things differently. And then I can test whether this relationship that came out of this data was actually useful. Graphical models. So we don't actually need data for there to be a model. Just drawing a graph is a useful model. On the left-hand side of the screen, this is a model of what would happen with exercise intensity and oxygen consumption. This is depicting that as your intensity of exercising increases, your body's rate of oxygen consumption is going to increase until you hit a point. And that point they call the VO2 max point. If you keep exercising more intensely, your body's physiology, its metabolism changes, and you cannot consume more oxygen. And so in order for you to exercise more intensely, your body has to resort to other methods, other metabolic pathways that may not involve using additional oxygen, or your exercise intensity may just hit a wall and you may not be able to hit any more in increases. And so what's interesting here is they've put little dots on this line. There's no reason for these red dots to be there. They could have just drawn the line, but the dots themselves are a model of what if you took data from a real person. Then the data, they're saying it would fall around, it would cluster around this line. That's what they're modeling by putting the dots there. What if we took data? So the line itself is modeling the theory that there is a VO2 max point, and we can go out and gather data and test this theory. But then the dots model then what we would predict to happen if we went out and ran the experiment. So there's all sorts of interesting ways graphs can be used to communicate. Models communicate just the same way a picture of somebody with a jacket on their shoulders can communicate ideas. Predator-prey cycles over here as well. Rather than me talking out what might happen with wolves and rabbits, if you introduce them into a habitat together, I can draw graphs that sort of say, well, when there's low populations of wolves, you'll get higher populations of rabbits, and that'll cause the population of wolves to increase as the population of rabbits decrease, and you'll get these oscillations over time. And so I can draw that out in a graph, and then we can go out and test it. So let's go into an area where we know that we've got these two predator-prey and see if we do get these cycles. So graphs can represent hypothetical relationships. Laboratory models can be physically instantiated, like the mouse model, also like a human model. This woman who's in this respirometry setup on the left-hand side there, she might have come in to learn about something about herself, to say, you know, I'm not feeling well, I want to test to see, you know, what if there's anything wrong with me. Or she herself might be a subject in a study where data on her is going to be used to make inferences about the human population in general. So there's different ways in which physically instantiated models can be used. But in general, we're asking these what if questions of what if we put these physical systems or, you know, natural biological systems under these particular conditions, what would happen to them? And what does that kind of tell us about the underlying systems? And then getting closer to what we worry about as industrial engineers is models unleashed in the real world. So this is an intersection that has no stoplights. And I could ask you, what would happen if you had a lot of traffic coming into an intersection without any stoplights? And some of you might say there would be crashes, there would be wrecks, you know, things like that. We come up with all of these different ideas. And then we could go out and test those ideas. But then I could show you this picture, and I could sort of point out that there's this like weird circular traffic flow that's kind of happening here. And on one hand, it looks like a major traffic jam. This is not an efficient way to route traffic. But on the other hand, this isn't necessarily what I expected. So looking at this image gives me new ideas of thinking about self-organized traffic flow in human systems. Now, does this generalize? Could you go anywhere else in the rest of the world? Probably not. My dad, who was a lawyer, when he was in law school, would talk about, in law, they would talk about if there were studies where you'd have people stop at red lights in the middle of the desert in different countries, and you saw which country would wait for the red light to turn green and in which country people would just go through the red light. And there were stark differences, cultural differences. And so, you know, so just kind of to show that even the idea of having a stoplight, you know, people's opinions about whether they should follow the stoplight, you know, is going to vary. So these things You know, traffic is something you have to be very careful about. When something works in one area, does it generalize to another area? But it at least provides a model for how things potentially could work and enhances our thinking about this. And this is something that we effectively, a real traffic intersection became a model for us to think about. And so, you know, how generalizable are these things? The Titanic is another great example of this. People learned so much about these ships through the Titanic. There are still studies, you know, being written, you know, saying that, well, we misunderstood exactly what happened with the Titanic. It turns out that it wasn't just that they hit an iceberg, but the metals that they were using in the waters, in the cold waters that they were much more brittle in those waters than they were in the conditions in which the ships were put together. And they made those things, you know, much more fragile. And so we wouldn't have learned that if it wasn't for these models being out in the wild. And so when we start putting your technology into the world, then you start wondering about informed consent. When we do studies here at the university, we have to make sure that we bring subjects in that they give their informed consent. When you release a new car onto the roads, somebody gets in that car, they don't realize that you are probably learning from them. Think about all the data that Tesla gathers from every Tesla driver, you know, but even in things less sophisticated, just, you know, a normal Toyota, you know, vehicle that's not connected. You know, if you get a bunch of vehicles after you've installed a new type of braking system and they get into crashes, you've learned a lot about that braking system at the expense of the people that were driving that car. So real world models, they do more for us than what the laboratory models can. So we in this class are trying to build things in between the laboratory models and those real world models. We are trying to build artificial models that have much more realism than a mathematical model or sort of a basic laboratory model, but are much safer to experiment with than experimenting in the real world. And our models will be simpler than the real world models because we want to try to use them to gain insights and also increase generality or generalizability. So if we tailor a simulation model to be exactly like ASU's campus, then anything we learn about that simulation model will only apply to ASU. If we want to sort of say something more broadly about university campuses in general, we may need to make a more simplistic model that allows it to be more generalizable across a wide range of campuses that we're running our inference on. And I can take this to an extreme with things like board games. So like the game of Monopoly over here, you know, this is overly simplistic. You know, there is a jailer, you know, you can go to jail down here, but there's no police. So this is a model of a city that has jails with no jailers. And yet it doesn't need to have that because really it is a model of how real estate works. And you might say, yeah, but it's just a board game. But a little kid is going to learn so much about real estate that that little kid didn't understand beforehand after playing this game. So this is much better than nothing. And then that little kid might grow up to become a real estate tycoon or even president of the United States, you know, and for all we know, the seeds of that knowledge might have come from working with a real estate model like this board game here. And so we take the salient features out of the systems we're interested in, the important salient features, not all of the features, just the salient ones. So we got rid of the police. All we need to know is that a jail existed. We don't care about the dynamics of the police. And then we experiment with the simplistic models, and that gives us insight for action that we can make back in the real world system. And that's what we're trying to do. We're not trying to make realistic models, we're trying to make insightful models. And what's cool about that too, is that we also can use these models to communicate with each other. And so you can take your mental models that are hard to describe verbally, you can put them into a simulation, and then that simulation helps you formalize, just like drawing a graph helps you formalize an idea that you can communicate to others. And so others on your project teams, for example. And then those others can then say, ah, I see what you did there, but I don't think I agree with your assumption you made here. And then they can go in and change that. And they have now communicated with you their background expertise and incorporate that into a model. So all these simplistic models allow us to communicate with each other in a way in which, just say, verbal explanations do not. But we always have to run the risk that we might have to be very careful that we're not overlooking some simplification that makes the model that we're all building around totally unrealistic. So we might think these are good models for the clothing, and maybe the clothing is fine, but the model that they're hung on maybe isn't a representative sample. Two white people who are extremely fit and very well done up may not be the best representation of the demographics that we imagine that these clothes are going to be worn by. So we have to be very careful of this, because in simulation, we can inadvertently do this. We can build a bad fashion model in simulation, but we can do it unintentionally, and we have to be able to spot it. All right, so let's do a couple of exercises here. So let's look at this. And so in the chat, just the next 30 seconds or so, you just give me a stream of consciousness of what do you see when you initially look at this image. Anything, just give me a word, a couple of words. This is excellent. This is good. So I see 2 triangles, 3 circles, triangles and circles. Anybody else? Do you see anything else? Are there cartoon characters that this reminds you of? Is there a story? Pac-Man. I see a lot of Pac-Man. Illuminati. That's interesting. The white triangle, top of a building. I see a lot of black and white. Gotcha. Top. Yeah, got the top of a building. Star. I see star. These are excellent. Modern table. Conflict, very abstract. This is beautiful. All right, so just looking at a couple of these, like star. I'm pretty sure the reason someone saw star is if you look here, that if you kind of trace the outline that I'm doing with the mouse, that you can kind of see that there is a 1, 2, 3, 4, 5, 6 pointed star that somehow could be overlaid on top of this and would line up to this. And that's very interesting. But if you actually look at the lines on a page, there is no star that was drawn there. So your mind filled in, your mind answered a question of what the heck is being represented here? How was this created? And a star came into mind, like, oh, well, maybe there's a star here, but the star got erased. So again, you're starting to fill in, and you're answering what if questions with your mental models. Pac-Man. So you look at this. So if you're familiar with a Pac-Man video game, that this here looks like a Pac-Man. I once had students in this class give me a beautiful narrative about 3 Pac-Men converging on a center of a bad guy that's covered, and hidden under, like, it was this whole huge narrative of like what was going on, all from this little image of a couple of lines and some splotches. I've seen, people talk about tables, conflict. That's another one, like, I get it. Like, I see conflict here, but I have no idea why. I cannot tell you why I see conflict here, but I get it. I guess, yeah, this is a good one for conflict. Maybe because the 3 Pac-Men look like they're about to attack each other in an arena. I don't know. But this is showing that our mind is trying to answer causal questions. Our mind is filling in with these mental models that are making use of our experience. My guess is if you look at this picture, your mind will immediately jump to things. My guess is most of the people, when you look down here, you'll see what I'm guessing most of you view as a circle that's being cut out underneath a man, and by someone underneath that circle with a saw. And that's, but if you actually look at the proportions here, the thing that is on the floor, which isn't even a closed loop, but if it was a closed loop, it wouldn't be a circular loop, it would be an oval. And you'd say, oh, but the man's staying on, we're at a different perspective and all these things. It's like, but yeah, but the drawing is of an oval. So you are filling in with your mental models that there's a camera, it's got a perspective, there's an angle of the floor, and so on and so forth. There's no motion that's being shown in this still image, and yet we think of this saw as being moving up and down. My guess is that some of you, when you look at this depiction of a man, for one, you believe it's a man, but you know, the proportions on this is not exactly human-like. It's like sort of this like really big nose, and I have a very, you know, big nose, and you know, that I'll admit, but it's nowhere in the size of this one. You know, this one, he's got this like really tiny head. Like, this is not a human head, and yet I think we're all okay with saying this is a human man. My guess is that a lot of you don't like this man. When you look at this man, you might say that he deserves what's coming to him, you know, because he's arrogant or whatever these things. This poor guy, we haven't even met the guy. We don't know what he says. It's just a snapshot of him in time, and yet it can communicate so much. So, and that's all coming from your mental models filling in these gaps, answering these questions. Same thing, and I'll skip through this kind of a little more quickly. This is sort of a famous piece of art where tandem convergent, tandem divergent. This is a model for fiancés, a model for couples just before a divorce. So here you see the front bike tires are joined together. Here the back bike tires are joined together. Here you're seeing a depiction of what it's like to be with someone and be as close to them as possible and only wanting to be closer. Whereas in the bottom one, you see something where you're with someone that you want to be nowhere but apart from, and you can't get away from them. And so these supposedly are depicting bicycles, but in reality, they're depicting a condition that I think we all could probably understand without even having to build such a bike. So you know, someone actually has built this bike. You can see this, but I don't have to get on this bike to know that it's not going to work. And I don't have to build the bike to understand what's being communicated here about relationships, about human relationships. And so again, filling in with our mental models. Even things like, so well, how do we develop these mental models over time? We start with some mental model, like you get on this boat and somebody says, all right, you steer. And you go to the back of the boat and you grab it and you might try to steer the boat left. And if you've never been on such a boat, then you think left, all right, I'm gonna push the rudder left. But if you push that rudder left, the boat turns right. Things get reversed. And so you end up having to quickly update your mental model. If you've ever seen the movie Independence Day with Will Smith, he's put into an alien vehicle that he has to fly. And someone has put the instructions for which direction is forward and backwards on upside down. And he initially tries to move forward and he goes backwards and hits the back of the area that's holding the vehicle in. And then he says, some jerk, he flips it around and then he's fine. And then he can fly the vehicle. So he has a mental model on what would happen. What if I were to take this rudder, you know, and turn it one way or another? How would the boat work? And your mental model helps you answer that what if question. You then test it in the real world, and then you update that mental model. So your mental models are constantly being updated with your personal experience. And that's what makes them so strong. The downside of these mental models is that they're very bad at handling dynamic situations, complex situations, and dynamical and situations of a lot of different parts. And on top of that, the way in which the kind of experience of a community changes over time affects how those mental models work. So as an example, there's this famous example I've put on the left side of the screen. A man and his son are driving in a car one day. They get hit. They get into a fatal accident. The man is killed instantly, but the boy is knocked unconscious. He's still alive. He is rushed to the hospital and needs immediate surgery. The doctor enters the emergency room, looks at the boy and says, I can't operate on this boy. He is my son. Now, when this was given to people, say in the 70s, people could not wrap their head around the scenario here. It seemed like a paradox. My guess is that most of you, when you read this, do not have any problem with this. Now, older audiences, when they read this, their mental model of a doctor is that their mental model of a relationship was a heteronormative relationship, man and woman, and their mental model of a doctor was that doctors could only be men. If that is your mental model of the world, you cannot make sense of these data, because that, you'd say, but the man was killed. So how, if the man was killed and the doctor's and then the doctor must have been the father, but then that would mean the doctor was killed, and it would just seem like it wouldn't make any sense. Of course, one answer is the doctor is his mother. Another answer is the doctor is his other father, in a homosexual relationship. And so these are new ways in which these mental models have changed over time and help make people more equipped at understanding these sorts of things. And so the question really is, without asking you what you thought initially, how useful was your mental model to making sense of these data? And so that's kind of what we're saying here. Mental models, you're making use of all of your lifetime experience. The problem with that is it becomes difficult to communicate to someone else who has a different lifetime of experience. Somebody from the 70s can't communicate to someone who was born, say, 20 years ago, why that situation seemed like a paradox. Somebody, probably most of you that are sitting in the class or at home right now, probably have no trouble with that and can't even understand the world in which somebody in the 70s was in that would have a problem with that. So, and on top of that, just in general, once you add complexity, a lot of moving parts, these mental models that are so powerful and so important because they have so much experience become so useless. So we want to choose quantitative models, and that's what we're starting to do in this class. And so mathematical models, these are the models you'll see in a lot of your OR classes. So, these are models, stochastic OR, deterministic OR. These are better at handling complexity and dynamic change. They are easier to communicate with others because you can write them down and you all can agree on what's on the page. But they may incorporate very little information about the systems being modeled. So they are highly simplistic. They give up a lot of the realism. And so you go from a world of experience inside a mental model down to 2 or 3 assumptions that you can then use to write out a couple of equations. And so one approach to these quantitative models are mathematical models, which are kind of the worst of all of this, where you get a couple of equations out, and then even with only a couple of equations, you maybe only can solve for the steady state conditions. A lot of what you do in 470, stochastic operations research, is you're studying for steady state limits of queuing systems, for example. So you have no idea what's going to happen up to steady state. Like maybe there's going to be a huge amount of traffic that's going to then dissipate and things will settle out. And and you really might care about that initial burst of traffic that isn't properly handled before things kind of settle out. But maybe all the models that you're using are focused on just what's happening in that steady state. So that can be a downside of that. You can fix that by saying, all right, I'm going to give up on a lot of those Little's Law and some of those other simplifications that we have, and I can study things numerically. So I can actually allow myself to, say, in a spreadsheet, I can write down a dynamical formula for how things are going to evolve over time and then plot them out. And that helps us understand graphically how dynamical systems work over time. And it's good for communicating in terms of these graphs. But if somebody then says, well, actually, can you add in another teller in the bank simulation, or your bank, can you take away a teller? Can you change the inter-rival distribution to a different way? It becomes hard to sort of, in these numerical models, and usually you implement something like a spreadsheet, it becomes very hard to make those changes quickly. And so that's why we end up using simulation models like the ones in this class, where these are tools that are fast, they're approximate, they are not analytical, they don't produce mathematical answers, but we use math to build them. They're very flexible, so you can go in and you can easily change components and swap them out and swap new ones in. And they're good for communication because you can actually see how things are wired together. So you can build a simulation model like this one, and you can end up seeing a graph. And so it kind of becomes much clearer how things are connected together. The downside is that we are going to lean heavily on software that allows us to do this. And we are hoping that the software developers haven't made assumptions that will end up invalidating the models that we end up building. So a lot of companies end up using these models. Southwest does a lot of simulation modeling for how people see planes, for how they end up putting cargo on planes. There's some great examples of that. More related to today, there are simulation models that help figure out how you board a plane affects how diseases spread on planes. And these would be very difficult things to handle with a mathematical model, but are very easy to handle with simulation models. And they're so realistic that they're hopefully very, and yet not too realistic, that you can generalize across a wide range of different types of planes and boarding styles. So these are just kind of summaries from these types of research. So closing out here, simulation is more than just programming. This is not a programming class. This is a class that is going to combine math, stats, and programming into one. And our main challenges that we need to solve is to provide useful insights without getting too complicated, too realistic, and reduce the execution time so that our computer sims can actually run in an amount of time that makes them useful in themselves, usable. And we have to use good statistical methods in both cases. So that's what we learn how to do here. So we're going to combine all of that into one in 475. We're going to focus before the midterm on the mathematics and probability of building these models. After the midterm, we're going to focus on the stats of how do we then make use of these models. And then during the lab, we are going to focus on actually practicing with these tools. So because I'm 11:43, I will, let me get to the attendance question, and then I'll be happy to take questions after that. These are the same reminders from the before. Again, there's an ICA that is due before the next lecture. It's very short. Lab 1 is out there, so is homework B1, and the next set of ICAs are also available. All right, so I want to get the attendance exercise out there, then I'm happy to open things up for any questions you have. So again, visit this site. It'll take you to a Google form. There will be 10 answers. You only need to fill out one because we only had one attendance question today. On other days, if there's multiple answers, you'd fill out multiple lines. And at the end of class, you hit submit. The attendance exercise for today is, what is the question that models help us answer? So I said there's a simple definition of any type of model, be it a math model or a fashion model. And I'll put that in the chat as well. And so it is, so the attendance question is, what question do models help us answer? And you just have to put that into this attendance exercise and hit submit. And you'll have to log in with your ASU account in order to get access to this. For those, for all of you, I check this in 24 hours after the video from today is posted. And so you have effectively 24 hours to get that answer in. They're graded for completion. I'm just looking for a coherent answer, not for correctness. And that's all that I have for today. So are there any questions I can handle if that's all that you guys need, then you can feel free to log out. I will hang around for a couple of minutes. But, and I noticed some people are answering this in the questions field. Again, this is a different link than the link earlier. The 475 questions link, that was to ask me questions about the content during class. This attendance link is different than that. Answer your question at this attendance link, not in the questions link from earlier.
I have a question. I just scanned the QR code and it's coming with like 10 different questions that you can answer.
That's right. Just fill in the first one. It'll give you 10. Yeah, this is a generic form I'll use every class. And some classes will answer more questions, some less. And so if this was a class where I answered 3, then you would just open that up at the beginning of class. You'd put the first one in, the second one, the third one. At the end of class, you'd hit submit. So I just leave room for me to ask a different number of questions.
Okay.
All right, any other questions?
Yeah, when I scan the code, it says you need permission. I'm not sure what to do.
You need to make sure that you log in with your ASU ID. So if you're getting that, it may have tried to log you in with a Gmail account that you have. And there should be a button somewhere, either in the top right or maybe just below that error message that says switch account. and you should be able to switch to your ASU account, and then you'll get access.
There's nothing in there. It's just Google Docs.
All right, well, in that case, so again, in Google Docs, there's usually an icon in the upper right that is associated with your account. And if you click on that, you can then choose a different account. If you go to Google Docs, if you just go to drive.google.com, for example, you can then log in with your ASU account. Again, if it's already logged into your Gmail account, you can use in the upper right, you can add an account and you can log into that. And when you're logged into that and focal, when that's been in focus, you can then go to this URL and you should be able to get access to the question. But you do need to log in. That's the way we get attendance, is it has to be tied to your ASU account.
Okay. Thank you. I'll try to doing that.
Okay. Again, you got 24 hours till after the video is posted. All right. Any other questions? Did you discuss lecture 0, lab 0 stuff? Are they quizzes? So I think you mean on Canvas, there are a couple of quizzes that you have to answer on Canvas in the kind of unit 0 that are just about the syllabus. And those, once you answer those and get a perfect score on all those unit 0 exercises about the syllabus and about the kind of ASU sync experience, then you'll be able to get access to all the other units. So do that, and then you'll get access to everything else. So go to Canvas, click on modules, go to unit 0, and make sure you've completed all of that. Great. Any other questions? All right, so with that, I will end the meeting and see everybody on Thursday.
One last
Yep.
question. This is showing me you need permission, and that's what I'm getting. I'm not sure if you can see it. It's just that this form can only be viewed by user in the owner's organization. And
right, the ASU. So that means that you are accessing it as under your Gmail account, and you'll need to switch to your ASU account. And so sometimes on those authorization pages from Google, down I think in the middle there's a hidden like switch account. If not, you'll have to go to Google Docs separately, log into your ASU account, make sure you're logged in, and then you can go to this URL. But you should be able to switch the account, but that just means you're not logged into your ASU account on that browser on your phone.
Okay, thank you.
All right, so with that, I will end the meeting and see everybody on Thursday. Have a good day. Oh, and don't forget, there is a lab on Wednesday. You don't have to attend the in-person lab. It's all online, but if you want to, the TA said he will be available at Brickyard M111, but you shouldn't need any of the software to complete the lab.